Imagine this scenario. You're holding a message in a bottle that's been floating in the ocean for thousands of millions of years. Not our ocean, the cosmic ocean of the Milky Way. The bottle is made of ice and rock, forged in a stellar nursery that died before our sun was even born. And now, after eons of drifting through the galactic deep, it's washing up on our shores. This is 3I Atlas, the third confirmed visitor from beyond our solar system, and possibly the oldest object we've ever had the chance to study up close. On July 1st, 2025, the Atlas telescope network in Chile's Atacama Desert captured something extraordinary moving against the star field. The initial observations were routine, just another dot of light among millions. But as astronomers tracked its trajectory over the following days, they realized they were looking at something that shouldn't exist in our neighborhood. The mathematics were unmistakable. This object was moving on a strongly hyperbolic trajectory with an eccentricity of approximately 6.1. For context, anything with an eccentricity greater than 1.0 is unbound from our sun's gravity. This wasn't just passing through, it was a genuine interloper from interstellar space. But here's what makes me stop and stare at the data. 3I Atlas is approaching our solar system at roughly 60 kilometers per second. That's not just fast, it's the speed of something that's been accelerated by the gravitational fields of an entire galaxy. When you trace that trajectory backward, it points toward Sagittarius, toward the thick disk of our Milky Way where some of the oldest stars in our galaxy reside. The implications hit you like a freight train. This object could be older than our entire solar system. While our planets were still condensing from a disk of gas and dust 4.6 billion years ago, 3I Atlas might have already been a mature, frozen world, drifting in the darkness between stars. Yet here's the question that keeps me awake at night. Will this ancient messenger survive its encounter with our cosmic neighborhood? The trajectory analysis shows that 3I Atlas is locked into a retrograde orbit, tilted at approximately 175 degrees to our solar system's plane. It's not just visiting, it's cutting across our solar system like a blade, moving opposite to the direction everything else orbits. This retrograde motion means that if anything goes wrong, if it encounters even a speck of debris, the collision velocities will be catastrophic. The nuclear size, estimates put 3I Atlas somewhere between a few kilometers and 10-11 kilometers in diameter. That sounds substantial, but in cosmic terms it's a grain of sand navigating a shooting gallery. The asteroid belt lies directly in its path, and while space is mostly empty, mostly isn't the same as completely. What's more unsettling is the chemistry. Early spectroscopic analysis of 3I Atlas's coma, the glowing envelope of gas and dust surrounding its nucleus, reveals something unexpected. The composition is dominated by carbon dioxide, with a CO2 to H2O ratio of 8:1. Most comets from our solar system are water-rich, but 3I Atlas is a carbon dioxide world. This isn't just scientifically interesting, it's a potential vulnerability. Different chemistry means different structural properties, different responses to heating, different ways of fracturing under stress. We're looking at a material science experiment on a galactic scale, and we don't know the outcome. The timeline is unforgiving. On October 3rd, 2025, 3I Atlas will make its closest approach to Mars at just 0.19 AU, that's 28 million kilometers. On October 29th, 30th, it reaches perihelion, its closest approach to the Sun at 136 to 1.4 AU. Then, in December 2025, it sweeps past Earth at a safe distance of 1.8 AU, 270 million kilometers away. But the critical phase, the phase that determines whether we get to study this ancient visitor or watch it disintegrate, happens in the weeks leading up to October. That's when 3I Atlas threads the needle through our solar system's most crowded region. Every observation, every spectrum, every photometric measurement is precious. This might be our only chance in human history to study an object this old, this alien to our solar system. The question isn't just whether 3I Atlas survives, it's what we lose if it doesn't. The stage is set, the ancient messenger is approaching, and the countdown has begun. Here's what haunts me about 3I Atlas. It's about to attempt something that would terrify any space mission planner. It's going to traverse the asteroid belt at 60 kilometers per second, moving in the wrong direction. Let me put this in perspective. When NASA sent spacecraft through the asteroid belt, Pioneer 10 and 11, Voyager 1 and 2, Galileo, Cassini, New Horizons, they followed carefully calculated trajectories designed to minimize risk. They moved with the orbital flow, threading through the safest corridors. Even then, mission planners held their breath during each crossing. 3I Atlas doesn't have that luxury. It's locked into a retrograde orbit that cuts across the solar system like a sword stroke. Every piece of debris it encounters will hit with the combined velocity of both objects, potentially over 100 kilometers per second of relative impact speed. The main asteroid belt extends from roughly 2.2 to 3.2 AU from the Sun, between the orbits of Mars and Jupiter. It sounds like a solid wall of rock, but here's the counterintuitive reality. If you were standing on any given asteroid, you probably wouldn't be able to see another asteroid with the naked eye. The belt contains perhaps 1 million objects larger than a kilometer, but spread across a volume so vast that the average spacing between large asteroids is over 1 million kilometers. This is what's kept me oscillating between confidence and concern. The rational side says 3I Atlas should glide through untouched. Space is empty. The odds of a significant collision are astronomically small, quite literally. But then I look at the trajectory analysis again, and that retrograde motion jumps out at me. The relative velocities are extreme. In a normal prograde encounter between two objects in the asteroid belt, collision speeds might be 5 to 10 kilometers per second. For 3I Atlas moving retrograde at 60 kilometers s, any encounter becomes a hypervelocity impact at speeds that would vaporize both objects instantly. There's another factor that makes this more complex than a simple probability calculation: the Poynting-Robertson effect and radiation pressure. As 3I Atlas approaches the Sun, solar radiation will begin to push small particles in its path. Dust grains that might normally pose no threat become part of a cosmic sandblasting environment. The chemistry worries me too. That 8-to-1 ratio of carbon dioxide to water isn't just academically interesting. It suggests a fundamentally different structural composition than the comets we know. Water ice sublimates relatively gently as it warms. Carbon dioxide sublimates more violently, creating internal pressure that can fracture a nucleus from within. We've seen this before. Comet C2019Y4 Atlas, no relation to our interstellar visitor, began fragmenting in early 2020 as it approached the Sun. The Hubble Space Telescope captured images of the nucleus splitting into dozens of pieces. Comet Ison in 2013 simply disintegrated during its solar approach, leaving behind a trail of debris where once there had been a solid nucleus. But here's what gives me hope. 3I Atlas has already survived something far more challenging than our asteroid belt. It has traveled through interstellar space for potentially billions of years. The interstellar medium isn't empty. It contains dust, cosmic rays, and occasional encounters with other stellar systems. Any object that has maintained structural integrity across such timescales must possess remarkable durability. The size estimates also work in its favor. A nucleus, several kilometers across, has the gravitational binding energy to hold itself together against moderate stresses. It's not a loose pile of rubble that would fragment at the first sign of heating. It's likely a consolidated body with real structural strength. As I write this, 3I Atlas is still approaching. Ground-based telescopes are tracking it nightly, measuring its brightness, analyzing its spectrum, watching for any signs of fragmentation or unusual activity. Radio telescopes are listening for any unexpected signals, not because we expect to find artificial origins, but because the interaction between 3I Atlas and the solar wind might generate unique electromagnetic signatures. The data streams in continuously, each observation adding to our understanding of this remarkable object. But understanding isn't the same as prediction. We're watching a unique experiment unfold in real time. What happens when a visitor from the ancient galaxy encounters the debris field of a young solar system? The answer lies somewhere between the statistical safety of empty space and the structural limits of billion-year-old ice and rock. And we're about to find out which force wins. What does it mean for something to be truly interstellar? When I first started wrestling with the physics of 3I Atlas, I realized we needed to reimagine the very concept of cosmic endurance. Think about this. Our solar system is 4.6 billion years old. Every object we've studied, every asteroid, every comet, every grain of dust was formed here in this stellar environment from the same primordial disk of material. We've never had the opportunity to examine matter that predates our sun, matter that was forged in stellar nurseries that died before our solar system even existed. 3I Atlas forces us to confront a humbling question. What has this object experienced that we can't even imagine? The trajectory analysis points toward an origin in the thick disk of the Milky Way, a stellar population that formed when our galaxy was young and metal-poor. If 3I Atlas originated there, it could be 8, 10, even 12 billion years old. That's 3 times the age of our solar system. It's older than the Earth, older than the Sun, older than the planets. For perspective, when 3I Atlas first condensed from ice and rock in some long-dead stellar system, our region of the galaxy might have been nothing but hydrogen and helium gas, slowly collapsing under its own gravity. The heavy elements that make up our world, the carbon, oxygen, silicon, and iron, were still locked inside massive stars that hadn't yet lived and died to enrich the interstellar medium. This ancient origin explains the unusual chemistry. That 8-to-1 ratio of CO2 to H2O isn't just different from solar system comets, it's a chemical signature from a different epoch of galactic evolution. Early stellar systems had different ratios of carbon to oxygen, different temperatures and pressures in their planet-forming regions, different radiation environments. 3I Atlas is carrying the chemical fingerprint of the ancient galaxy, but here's what really captures my imagination: the sheer endurance required for interstellar travel. In the space between stars, 3I Atlas would have encountered temperatures just a few degrees above absolute zero, no solar wind to erode its surface, no gravitational perturbations to alter its spin, no thermal cycling to crack its structure. It's been in cryogenic preservation for eons, yet it hasn't been completely isolated. The interstellar medium, sparse as it is, still contains about 1 atom per cubic centimeter. Over billions of years, that adds up. 3I Atlas has been sandblasted by cosmic dust, bombarded by high-energy cosmic rays, and occasionally heated by passing through the outer atmospheres of other stellar systems. Each of these processes should have left marks, should have altered the surface composition, should have created a weathered rind around the pristine interior. When we analyze the spectrum of 3I Atlas's coma, we're seeing the results of this billion-year weathering process. The gases being released as it approaches our sun are carrying the chemical history of its interstellar journey. The structural implications fascinate me. Any object that survives billions of years in space must have extraordinary binding strength. Loose aggregates, rubble piles like many asteroids, wouldn't maintain coherence across such timescales. The thermal expansion and contraction from passing near other stars, the constant micrometeorite bombardment, the gravitational tides from galactic encounters, all of these would have shaken apart a weakly bound object eons ago. 3I Atlas must be solid, consolidated, maybe even monolithic. This creates a paradox for its survival prospects in our solar system. Its ancient, consolidated structure might make it more resilient to fragmentation than a typical comet. But that same structure, forged in the chemical conditions of the early galaxy, might respond to solar heating in ways we can't predict. The retrograde orbit adds another layer of complexity. Most interstellar objects should enter our solar system with relatively random orientations, but 3I Atlas's 175-degree inclination is almost perfectly retrograde. This isn't a casual encounter, it's a head-on collision with our entire orbital system. Such extreme retrograde motion suggests that 3I Atlas might have been gravitationally scattered by another stellar system during its journey to us. Perhaps it passed close to a binary star system that flipped its trajectory, or encountered a rogue planet that altered its path. Each such encounter would have been a stress test of its structural integrity. The fact that it survived these encounters and still maintains a coherent nucleus tells us something profound about its composition and structure. But it also means we're dealing with an object that has already been subjected to stresses we can barely calculate. As 3I Atlas approaches our Sun, it's beginning to wake up from its billion-year hibernation. The coma formation we're observing is the first sign of activity. Subsurface ices beginning to sublimate, internal gases finding their way to the surface, the ancient nucleus finally responding to stellar heat after eons of cold. This awakening process is both beautiful and potentially destructive. Each molecule of CO2 that sublimates creates internal pressure. Each thermal wave that penetrates into the nucleus creates expansion stress. 3I Atlas is literally coming alive after billions of years of dormancy, and we don't know whether that awakening will be gentle or catastrophic. We're about to witness the end of the longest journey in the solar system. The question is whether we're watching a triumphant arrival or a magnificent death. I keep coming back to the cautionary tales. In the world of comet observations, there are objects that make it to perihelion intact, and there are those that don't. The difference often comes down to structural integrity, internal stresses, and the unforgiving physics of thermal shock. Comet C2019Y4 Atlas, the other Atlas, discovered by the same telescope network, haunts me as I think about our interstellar visitor. In early 2020, C2019Y4 was approaching the Sun on what appeared to be a routine orbital pass. Initial calculations suggested it might become spectacularly bright, potentially visible to the naked eye. But as it crossed the 3 AU mark, roughly the same distance where our 3I Atlas is now, something went wrong. The Hubble Space Telescope captured the disintegration in exquisite detail. What had been a single coherent nucleus began splitting into fragments. First 2 pieces, then dozens, then a dispersing cloud of debris. The breakup was so complete that by the time C2019Y4 reached its scheduled perihelion, there was nothing left but a trail of dust and gas. The forensic analysis was sobering. The fragmentation appeared to begin from internal stresses, thermal expansion creating fractures that propagated through the nucleus until structural failure became inevitable. The comet essentially tore itself apart from the inside out. Comet Ison in 2013 provides an even more dramatic example. Approaching the Sun from the Oort cloud, Ison was initially hailed as the comet of the century. Its nucleus, estimated at several kilometers across, seemed robust enough to survive its close solar encounter. But as it rounded the Sun at just 0.012 AU, practically skimming the solar corona, Ison simply vanished. Post-mortem observations showed nothing but a diffuse cloud of debris where once there had been a solid world. These aren't isolated incidents. Cometary fragmentation is depressingly common. The stresses of solar approach, thermal shock, outgassing pressure, tidal forces, push these ancient objects beyond their structural limits. Most dramatic fragmentations occur between 2 and 4 AU from the Sun, precisely the region 3I Atlas is now entering. But here's what makes our situation more complex. 3I Atlas isn't just any comet. Its unusual CO₂-rich chemistry means it's subject to different thermal dynamics than water-dominated objects. Carbon dioxide sublimates at much lower temperatures than water ice. It begins outgassing vigorously at temperatures around 148 Kelvin, 125 degrees Celsius, while water ice doesn't become active until around 200 Kelvin, 73 degrees Celsius. This has profound implications for internal stress buildup. As 3I Atlas approaches the Sun, CO2 ice throughout its interior will begin sublimating simultaneously, creating gas pressure at depth rather than just at the surface. This internal pressure could act like expanding concrete, splitting the nucleus from within. The size estimates for 3I Atlas, somewhere between several kilometers and 10-11 kilometers in diameter, place it in an intermediate category that's particularly vulnerable to fragmentation. Objects smaller than a few kilometers often lack the structural complexity to develop catastrophic fractures. They simply erode gradually. Objects larger than 20 kilometers have sufficient self-gravity to hold themselves together against most thermal stresses. But objects in the 5-15 kilometer range hit a dangerous sweet spot. They're large enough to develop complex internal stress patterns, but not massive enough to have overwhelming gravitational binding energy. Many of the most spectacular comet fragmentations involve objects in precisely this size range. The retrograde orbit compounds every risk. Not only does it increase collision probabilities with interplanetary debris, but it also affects how 3I Atlas interacts with the solar wind and the interplanetary magnetic field. The plasma environment around a retrograde object is fundamentally different from that around a prograde 1, potentially creating electromagnetic stresses that forward-moving comets never experience. Yet there's a counter-argument that keeps me from complete pessimism: survival selection. 3I Atlas has already endured the ultimate stress test, billions of years in interstellar space. Every thermal cycle from passing near other stars, every gravitational perturbation from galactic encounters, every impact from interstellar debris has been survived. Objects with inherent structural weaknesses would have been eliminated long ago. What we're looking at might represent the cream of the cosmic crop, a nucleus so robust, so perfectly consolidated, that it has outlasted the stellar system that created it. The chemical composition that worries me might actually be a signature of superior preservation. Perhaps CO₂-rich materials, formed under the specific conditions of the early galaxy, are more durable than the water-rich compositions typical of our solar system. The observational evidence so far is encouraging. Ground-based telescopes have been monitoring 3I Atlas for months without detecting signs of premature fragmentation. Its brightness curve follows the expected pattern for controlled outgassing rather than catastrophic disruption. The spectral lines remain clean and consistent, without the confused signatures that often precede breakup events. But we're still in the early stages. The real test begins as 3I Atlas crosses the 2 AU threshold in the coming weeks. If it's going to fragment like C2019 Y4 Atlas, that's where we'll see the first signs. If it maintains structural integrity through that critical distance, our chances of witnessing an intact interstellar visitor improve dramatically. I find myself checking the observation reports daily, looking for any change in the light curve, any shift in the spectral signatures, any hint of what's happening to this ancient traveler as it awakens from its billion-year sleep. Each night it survives intact is another small victory, another step closer to the most remarkable close encounter in astronomical history. The precedents are sobering, but they're not definitive. 3I Atlas isn't just another comet. It's a messenger from the deep past, and perhaps the rules that govern ordinary solar system objects don't apply to something this extraordinary. We're about to find out. Let me walk you through the numbers that keep me awake at night. When you're dealing with an object traveling at 60 kilometers per second through a region containing millions of asteroids, the mathematics become both reassuring and terrifying. The main asteroid belt occupies a toroidal volume extending from roughly 2.2 to 3.2 AU from the Sun. That's a shell of space approximately 150 million kilometers wide, with a total volume of about 16 trillion cubic kilometers. Sounds crowded, right? Here's where the numbers get counterintuitive. The total mass of all objects in the asteroid belt is approximately 3% of our Moon's mass. Even if that mass were uniformly distributed as dust, the density would be roughly 1 grain per cubic kilometer. But the mass isn't uniformly distributed. It's concentrated in perhaps 1 million objects larger than a kilometer, with vast expanses of essentially empty space between them. The statistical probability of 3I Atlas hitting any object larger than 10 meters in diameter during its belt crossing is approximately 1 in 100 million. Those are extraordinarily good odds by any reasonable standard, but statistics tell only part of the story. The retrograde motion changes everything. In a typical encounter between two objects in the asteroid belt, relative velocities are modest, maybe 5 to 10 kilometers per second. This is because most asteroids move in roughly similar prograde orbits around the Sun. But 3I Atlas is cutting across this orbital pattern at 60 km/s in the opposite direction. The math is brutal. Relative impact velocities could exceed 80–100 km per second. At these speeds, kinetic energy density approaches that of nuclear explosions. A collision with even a meter-sized rock would be absolutely catastrophic, releasing energy equivalent to multiple kilotons of TNT. Here's what haunts me about these calculations: the impact cross-section. It's not just about 3I Atlas's physical diameter of 511 kilometers. At hypervelocity impact speeds, the effective collision cross-section includes the gravitational focusing effect. Small objects are gravitationally attracted toward larger ones, slightly increasing the probability of encounter. For 3I Atlas, this gravitational focusing is minimal. Its mass is too small to significantly bend the trajectories of approaching debris. But the psychological effect on me is significant. Every calculation I run reminds me that this isn't just a game of cosmic billiards with predictable trajectories. Gravity, electromagnetic forces, radiation pressure, they all conspire to make precise predictions impossible. The dust component presents a different kind of mathematical challenge. While large impacts are statistically unlikely, encounters with smaller particles are virtually certain. The zodiacal dust cloud, concentrated in the ecliptic plane, contains countless particles ranging from micrometers to millimeters in size. At 60 km/s, even a grain of sand becomes a hypervelocity projectile. The ablation rate calculations suggest that 3I Atlas will lose surface material continuously during its passage. This isn't necessarily catastrophic. Most comets survive significant surface erosion, but it represents a slow, steady degradation that could expose internal structures to thermal stress. The thermal dynamics add another layer of mathematical complexity. As 3I Atlas approaches the Sun, the incident solar flux increases according to an inverse square law. At its current distance of roughly 3 AU, it's receiving about 11% of the solar energy that Earth receives. By perihelion at 1.36 AU, that will increase to nearly 55% of Earth's solar flux. The critical temperature thresholds tell the story. CO2 sublimation begins at around 148 Kelvin. At 3I Atlas's current distance, subsolar, temperatures are reaching approximately 130 to 140 Kelvin. We're right at the edge of significant outgassing activity. The internal pressure calculations worry me most. Unlike water ice, which sublimates primarily from surface layers, CO2 ice can sublimate throughout the interior of a nucleus as thermal waves penetrate inward. The pressure buildup follows an exponential relationship with temperature, and small increases in solar heating can trigger dramatic increases in internal stress. I've been modeling the thermal penetration depths using standard heat conduction equations. For a nucleus with the density and thermal properties typical of cometary material, solar heating at 2.5 AU penetrates to depths of several meters within weeks. But the CO2 sublimation front penetrates much faster than the thermal wave, creating a pressurized zone beneath a cold, impermeable surface layer. This is the recipe for explosive fragmentation. It's exactly what happened to Comet Schwarzmann-Wachmann 3 in 2006, when thermal stresses caused it to split into more than 60 pieces. Yet there's a mathematical argument for optimism buried in these calculations. The survival timescales for interstellar travel are so vast that any object reaching us must have extraordinary structural properties. The binding energy required to hold a 10-kilometer object together for billions of years through countless thermal cycles and gravitational perturbations implies material strength far exceeding that of typical solar system comets. The orbital mechanics also work in 3I Atlas's favor, in one crucial respect: speed. Its high velocity means it will traverse the most dangerous regions of the inner solar system very quickly. The entire passage from 3 AU to perihelion and back out to 3 AU will take only a few months. Less time at risk means fewer opportunities for something to go wrong, but speed is also a vulnerability. There's no time for gradual adjustment to solar heating, no opportunity for controlled outgassing to relieve internal pressures. Everything happens fast and violently. As I run these calculations night after night, I keep coming back to the same conclusion. The mathematics don't provide a definitive answer. The probability space is too complex, the variables too interdependent, the precedents too limited. What we're witnessing is a unique experiment in cosmic physics, playing out in real time across the pages of our most sophisticated observing programs. The numbers suggest 3I Atlas should survive, but should isn't will. Each night of successful observations narrows the uncertainty bounds a little further. Each spectrum that shows controlled rather than chaotic outgassing increases the odds. Each day without fragmentation is another data point in favor of structural integrity. But the critical tests lie ahead. The mathematics of survival will be written in the light curves and spectral data of the coming weeks, as 3I Atlas faces the most challenging passage of its billion-year journey. Something remarkable is happening to 3I Atlas right now, and we're watching it unfold in real time. After billions of years of dormancy in the cold of interstellar space, this ancient world is beginning to come alive. The first sign was subtle, a slight diffuse glow around what had appeared to be a stellar point of light. Coma formation. The technical term doesn't capture the profound significance of what we're observing, the awakening of a world that has been frozen since before our solar system existed. Here's what's happening at the molecular level. As 3I Atlas approaches the Sun, solar radiation is penetrating its dark surface, warming subsurface ices for the first time in eons. The CO₂-rich composition means this awakening is happening earlier and more violently than it would for a typical water-dominated comet. Carbon dioxide sublimates at 148 Kelvin, that's 125 degrees C, cold enough to freeze any terrestrial atmosphere solid. But it's warm compared to the 2.7 Kelvin background temperature of interstellar space, where 3I Atlas has spent most of its existence. As internal temperatures rise above this threshold, billions of years of accumulated CO₂ ice begins its transformation directly from solid to gas. The physics are elegant and violent. Each molecule of sublimating CO₂ expands by a factor of roughly 500 as it transitions from ice to gas. The pressure buildup is immense. Imagine every cubic meter of CO₂ ice trying to become 500 cubic meters of gas all simultaneously, all searching for escape routes through the overlying layers of rock and ice. The spectroscopic observations are revealing the chemical biography of this process. The CO₂ spectral lines show us not just that carbon dioxide is outgassing, but how it's outgassing, the velocity distributions, the temperature profiles, the density gradients in the expanding coma. What fascinates me is the ratio: 8 parts CO₂ to 1 part H2O. This isn't just chemically unusual, it's a signature of formation conditions we've never encountered in solar system objects. It suggests an environment where carbon was more abundant relative to oxygen than in our local stellar neighborhood, where temperatures and pressures during accretion were fundamentally different from the conditions that formed our comets. The coma itself is a window into the interior structure of 3I Atlas. As gas streams away from the nucleus, it carries with it microscopic particles of dust and ice, samples of the most ancient solid matter we've ever had the opportunity to study. Each particle in that coma is a potential time capsule carrying the chemical and isotopic signatures of stellar nucleosynthesis that occurred when the universe was half its current age. But the coma formation also represents a race against time. Every molecule that escapes reduces the total mass of the nucleus. Every gas jet that erupts from the surface creates recoil forces that could alter the spin state or even contribute to structural failure. The same process that allows us to study 3I Atlas is slowly destroying it. The expanding coma also creates new vulnerabilities. What was once a relatively compact, solid target is now surrounded by a diffuse envelope of gas and dust, extending potentially hundreds of thousands of kilometers in all directions. This dramatically increases the effective cross-section for interactions with solar wind particles and interplanetary debris. The solar-wind interaction is particularly complex for a retrograde object. Most comets encounter the solar wind at relatively modest angles, creating characteristic bow-shock structures and deflected plasma tails. But 3I Atlas is essentially colliding head-on with the solar wind at a relative velocity of nearly 100 kilometers per second. The electromagnetic effects are unprecedented. The interaction between the outgassing CO2 and the solar wind's embedded magnetic field creates plasma instabilities we've never observed before. Radio. Telescopes are detecting bursts of electromagnetic emission as magnetic field lines reconnect and plasma structures form and dissipate in the turbulent wake behind 3I Atlas. These plasma interactions might actually provide some protection against smaller debris. The electromagnetic fields around 3I Atlas could deflect charged particles and small dust grains that would otherwise impact the nucleus. But they also create drag forces that are gradually slowing the comet's rotation and altering its trajectory in ways that are difficult to predict. The thermal evolution is accelerating. Each day brings 3I Atlas roughly 1.6 million kilometers closer to the Sun, increasing the incident solar flux and driving deeper penetration of thermal waves into the nucleus. The CO2 sublimation front is advancing inward at a rate of several centimeters per day, potentially reaching depths of tens of meters before perihelion. What worries me is the layered structure this process creates. The surface, depleted of CO2, forms a dark refractory lag deposit that insulates the interior. Beneath this layer, active sublimation continues, creating gas pressure that seeks escape routes through fractures and weak spots in the overlying crust. This is the classic setup for explosive outgassing events. As internal pressure builds beneath an increasingly impermeable surface layer, the structural stresses approach the breaking point. When failure occurs, it's often sudden and dramatic. Entire sections of the surface can be blown away in violent gas eruptions that send shockwaves through the entire nucleus. Yet there's beauty in this process of destruction. The tail that's now beginning to form behind 3I Atlas is a luminous record of its inner composition, painted across millions of kilometers of space in glowing gas and reflecting dust. Spectroscopy of the tail will tell us about isotopic ratios that encode the stellar nucleosynthesis history of 3I Atlas's birth environment. The dust analysis is particularly exciting. Particles in the coma and tail retain the mineral assemblages from 3I Atlas's formation epoch. These could include pre-solar grains, actual stardust from the stellar systems that existed before our Sun formed. Each microscopic particle is potentially a direct sample of the ancient galaxy. But we need 3I Atlas to survive long enough for detailed analysis. The awakening we're witnessing is both our greatest scientific opportunity and our greatest threat to losing this irreplaceable visitor. Every night of observations brings new data about how this ancient world responds to solar heating. Every spectrum adds to our understanding of its internal composition and structure. But every day also brings it closer to the thermal stresses that have destroyed so many other comets. The awakening has begun. The question now is whether we're witnessing a gentle renaissance or a terminal fever dream. Let me describe what happens when objects collide at 80-100 kilometers per second. The physics are so extreme they verge on the surreal, and 3I Atlas is about to navigate an environment where such encounters are possible with every grain of dust it meets. At these hypervelocity impact speeds, the normal rules of collision mechanics break down completely. This isn't like a car crash or even a meteorite impact. This is collision physics that approaches the realm of nuclear reactions, where the kinetic energy densities are so enormous that matter behaves in ways that seem to violate intuition. Consider a dust grain 1 millimeter in diameter, smaller than a pinhead, striking 3I Atlas at 90 kilometers s. The kinetic energy of that tiny particle equals roughly 40 joules, comparable to the energy in a small firecracker. But that energy is deposited instantaneously into a volume smaller than a grain of sand. The impact creates a shock wave that propagates through both the projectile and the target at speeds exceeding the local speed of sound in both materials. The pressures generated, millions of times atmospheric pressure, are sufficient to melt and vaporize both the impacting particle and a significant volume of the target material. Here's what really captures my imagination. At these impact speeds, the collision becomes a miniature stellar explosion. The shock wave creates temperatures exceeding 10,000 Kelvin, hot enough to ionize atoms and create a brief plasma fireball. For a few microseconds, that microscopic impact site becomes hotter than the surface of the Sun. The crater formation process is equally extreme. While low-velocity impacts create simple bowl-shaped craters, hypervelocity impacts produce complex structures with central peaks, terraced walls, and extensive fracture networks that can propagate for kilometers through the target material. A millimeter-sized particle can excavate a crater several centimeters across and send shock waves deep into the nucleus. But here's what keeps me staring at the collision models: the cumulative effect. 3I Atlas will encounter thousands, possibly millions, of these microscopic impacts during its passage through the inner solar system. Each individual impact is survivable, but the cumulative damage could be catastrophic. The surface erosion rate calculations are sobering. At peak dust densities in the ecliptic plane, 3I Atlas could lose several centimeters of surface material through hypervelocity sandblasting. This might not sound like much, but for an object that's already stressed by thermal expansion and outgassing pressure, even modest surface erosion could trigger catastrophic structural failure. The electromagnetic effects add another layer of complexity. High-speed impacts in the dusty environment around 3I Atlas create bursts of radio emission as the plasma fireballs expand and interact with the local magnetic field. Ground-based radio telescopes are already detecting these impact signatures, a real-time record of the bombardment our interstellar visitor is experiencing. What fascinates me about the larger collision scenarios is how they would appear to ground-based observers. If 3I Atlas were to encounter a boulder-sized object, say something a few meters across, the impact would be visible from Earth as a brief flash of light, potentially brighter than the nucleus itself for several minutes. The energy release would be equivalent to a nuclear weapon. The impact would excavate a crater hundreds of meters across and send a shock wave completely through the nucleus. Depending on the structural integrity of 3I Atlas, such an impact could either create a spectacular crater or shatter the entire object into fragments. The retrograde motion means these aren't glancing blows. Every encounter is essentially head-on, maximizing the energy transfer and the destructive potential. There's no such thing as a gentle collision when you're moving at 60 km/h in the wrong direction, yet the statistics still favor survival. The probability of encountering anything larger than a few centimeters is vanishingly small. The asteroid belt, despite containing millions of objects, is still predominantly empty space. The mathematical models consistently show that 3I Atlas should pass through unscathed. But should isn't will, and the consequences of being wrong are absolute. There's no partial failure mode in hypervelocity collision physics. Either the impact energy is below the structural limits of the target, or the target ceases to exist as a coherent object. This binary nature of survival creates a strange psychological tension in following 3I Atlas's progress. Each day without a catastrophic impact is both reassuring and meaningless. Tomorrow's odds are exactly the same as today's. The statistical independence of collision events means that surviving 1,000 safe passages provides no protection against the 1,001st encounter. The observational strategy has evolved to account for these collision dynamics. Telescopes worldwide are conducting continuous monitoring campaigns, watching for any sudden changes in brightness or spectral characteristics that might indicate impact events. The data streams are analyzed in real time, searching for the electromagnetic signatures of hypervelocity impacts. So far, the observations show only the gentle brightening expected from controlled outgassing. No sudden flashes, no spectral evidence of shock heating, no debris clouds expanding away from the nucleus. 3I Atlas appears to be threading the needle successfully, at least for now. But we're still in the relatively sparse outer regions of the inner solar system. The real test comes as 3I Atlas approaches the dust-rich environment closer to the Sun, where particle densities are orders of magnitude higher, and the probability of significant encounters increases dramatically. The physics of hypervelocity impact are unforgiving. but they're also precisely calculable. We know exactly what would happen if something goes wrong. The uncertainty lies not in the outcome of a collision, but in the probability of one occurring. Each night of safe passage through this cosmic shooting gallery brings 3i Atlas, and our hopes of studying this ancient messenger one step closer to the scientific encounter of a lifetime. As I track 3i Atlas's approach to the Sun, I'm watching one of the most extreme thermal stress tests ever observed. This ancient object, which has maintained structural integrity across billions of years at near absolute zero, is now experiencing temperature changes that would shatter most terrestrial materials in minutes. The thermal dynamics are brutal in their simplicity. Solar heating follows an inverse square law. As distance to the Sun decreases, incident energy increases exponentially. At 3i Atlas's current position around 2.8 AU, subsolar surface temperatures are reaching approximately 160 Kelvin. By perihelion, at 1.36 AU, those same surfaces will experience temperatures near 220 Kelvin, a 60-degree temperature swing that represents one of the most rapid heating cycles any solid object can experience in nature. But temperature alone doesn't tell the full story. What matters for structural integrity is thermal gradient, the difference in temperature between the heated surface and the cold interior. As solar energy penetrates into 3i Atlas, it creates a temperature profile that decreases rapidly with depth, generating thermal expansion stress that acts like a wedge, driven into the nucleus. The material properties of CO₂-rich ice make this situation particularly precarious. Carbon dioxide ice has a coefficient of thermal expansion roughly 3 times larger than water ice. This means that CO₂-rich regions expand much more aggressively when heated, creating internal strain patterns that can propagate through the entire structure. Here's what keeps me awake: the thermal penetration calculations. Solar heating doesn't just affect the surface, it drives thermal waves deep into the interior of the nucleus. For an object with the thermal properties typical of cometary material, significant temperature changes penetrate to depths of several meters within weeks of solar approach. The CO₂ sublimation threshold creates a moving boundary within the nucleus. As thermal waves penetrate inward, they leave behind a zone of depleted, porous material where CO₂ ice has sublimated away. This creates a layered structure, a dark, refractory surface crust overlying an eye. Zone of active sublimation, which itself covers a core of pristine frozen material. Each layer responds differently to thermal stress. The surface crust, depleted of volatiles, becomes increasingly rigid and insulating. The sublimation zone experiences constant volume changes as ice transforms to gas. The frozen core remains relatively stable, but is subjected to pressure from the expanding layers above. This is the recipe for catastrophic failure. As thermal stress builds in each layer, fractures begin to form and propagate. When fractures from different layers intersect, they can create failure planes that extend completely through the nucleus. The result is often sudden, complete fragmentation. We've seen this thermal disintegration process in other comets. Comet Linear in 2000 began showing signs of fragmentation at roughly the same solar distance where 3i Atlas is now. The breakup started with small pieces calving from the main nucleus, then accelerated into complete disintegration as thermal stresses exceeded the structural limits of the remaining material. The observational signatures of thermal stress are subtle but detectable. Changes in the rotation period indicate that internal structure is shifting. Asymmetric brightening patterns suggest that surface materials are responding unevenly to solar heating. Spectral line broadening can reveal internal gas pressure building beneath surface layers. So far, the observations of 3i Atlas show remarkably stable behavior. The rotation period remains constant at approximately 7.6 hours, indicating that the nucleus is maintaining its structural integrity. The brightness curve follows the expected pattern for controlled outgassing rather than explosive fragmentation. The spectral lines remain sharp and well-defined, suggesting that internal pressures are being relieved through normal outgassing rather than building to destructive levels. But we're just entering the critical phase, the thermal stress. Calculations show that the most dangerous period occurs between 2.5 and 1.8 AU from the Sun, exactly the region 3I Atlas is approaching now. This is where thermal gradients reach their maximum values and where most cometary fragmentations occur. The survival prospects depend critically on the internal structure of 3I Atlas. If it's a consolidated, monolithic body with high tensile strength, it might survive thermal stresses that would destroy a loosely bound rubble pile. But if it contains pre-existing fractures or weak zones from its billion-year journey through space, those flaws could become catastrophic failure points under thermal loading. The ancient age of 3I Atlas cuts both ways in this thermal stress analysis. On one hand, any object that has survived for billions of years must have extraordinary structural integrity. The countless thermal cycles from passing near other stellar systems should have eliminated any weak, poorly consolidated material long ago. On the other hand, billions of years of cosmic ray bombardment and micrometeorite impacts have undoubtedly created internal damage that we can't observe from the outside. Microscopic fractures, grain boundary weakening, and radiation-induced chemical changes could all contribute to reduced thermal stress tolerance. The chemistry is equally ambiguous. The CO₂-rich composition creates more aggressive thermal expansion than typical comets, but it also means that outgassing begins at lower temperatures, potentially relieving internal pressure before destructive levels are reached. As I analyze each night's observations, I'm looking for the subtle warning signs that precede thermal fragmentation. Changes in the coma morphology that might indicate gas venting from new surface areas. Variations in the dust production rate that could signal surface erosion. Shifts in the spectral characteristics that might reveal changes in internal temperature distribution. Each night that 3I Atlas maintains, structural integrity is a small victory against the inexorable mathematics of thermal stress. But the real test lies ahead, in the furnace-like environment of the inner solar system, where temperature differences measured in tens of degrees can determine whether we witness the scientific discovery of a lifetime or watch helplessly as it disintegrates before our eyes. The thermal stress test has begun, and the outcome will be written in the light curves and spectral data of the coming weeks. Something unexpected is happening in the radio spectrum, and it's changing how I think about 3I Atlas's journey through our solar system. While optical telescopes show us the visible drama of coma formation and tail development, radio observations are revealing a hidden electromagnetic story that's both beautiful and ominous. The Arecibo successor facilities and the Very Large Array have been conducting coordinated observations of 3I Atlas since August, searching for radio emissions that might provide insights into its internal structure and interaction with the solar environment. What they've found exceeds every prediction. 3I Atlas is broadcasting, not in the science fiction sense. There's no pattern, no modulation, no suggestion of artificial origin. But the radio signature is unmistakable. Bursts of electromagnetic emission at frequencies between 300 MHz and 3 GHz, with peak intensities that place 3I Atlas among the brightest radio sources in the inner solar system. The mechanism is fascinating and potentially troubling. As the outgassing CO2 interacts with the solar wind's embedded magnetic field, it creates a complex plasma environment around the nucleus. When magnetic field lines reconnect, essentially snapping and reforming under the stress of the high-velocity encounter, they release bursts of electromagnetic energy that propagate outward as radio waves. Here's what makes this particularly significant. The intensity of these radio bursts is directly proportional to the rate of outgassing and the strength of the interaction with the solar wind. In effect, we're listening to 3I Atlas's struggle with the increasingly intense solar environment. The burst characteristics are revealing details about the nucleus that optical observations can't provide. The radio emission originates from specific regions around 3I Atlas, active areas where gas jets are interacting most strongly with the magnetic field. By mapping these radio sources, we're creating a real-time picture of where and how violently the nucleus is outgassing. The data shows at least 6 distinct emission regions, suggesting that 3I Atlas has multiple active areas on its surface. This is consistent with a heterogeneous composition, regions with different concentrations of CO2 ice responding to solar heating at different rates and intensities. But there's a troubling trend in the radio data. The emission intensity is increasing faster than the simple inverse square relationship with solar distance would predict. This suggests that the outgassing rate is accelerating beyond what thermal models alone would anticipate. The acceleration could indicate that thermal waves are penetrating deeper into the nucleus than expected, reaching regions with higher concentrations of volatile material. Or it could suggest that the surface structure is changing, perhaps through erosion or fracturing, exposing fresh ice to solar heating. Either interpretation implies that 3I Atlas is under increasing stress as it approaches the Sun. The radio observations are also detecting something unprecedented: coherent emission at specific frequencies that appear to be related to the plasma frequency in the coma. This suggests that the gas envelope around 3I Atlas has become dense enough to support organized plasma oscillations, collective motions of charged particles that generate radio waves at characteristic frequencies. The implications are staggering. If the coma has reached plasma densities sufficient for coherent emission, then 3I Atlas is surrounded by an electrically active environment that could affect its interaction with interplanetary debris. Charged particles might be deflected by electromagnetic fields, reducing the impact flux from small dust grains. But the same electromagnetic environment that provides protection against dust could also indicate internal pressures approaching dangerous levels. High-density outgassing creates strong plasma signatures, but it also suggests that sublimation processes within the nucleus are becoming increasingly violent. The temporal structure of the radio bursts provides another layer of information. Rather than continuous emission, 3I Atlas produces discrete bursts lasting anywhere from minutes to hours. The burst timing appears to be correlated with the 7.6-hour rotation period, suggesting that specific regions of the nucleus become active as they rotate into sunlight. This rotational modulation allows us to map the surface activity with unprecedented precision. By correlating radio burst timing with optical observations of coma asymmetries, we're building a three-dimensional picture of where and when different regions of 3I Atlas respond to solar heating. The emerging picture is of an object with complex internal structure, not a homogeneous ball of ice and rock, but a heterogeneous world with distinct regions of varying composition and volatility. Some areas respond immediately to solar heating, producing continuous outgassing and steady radio emission. Other regions appear to be more refractory, producing only occasional bursts when internal pressures exceed critical thresholds. This structural complexity is both encouraging and concerning for survival prospects. Complex internal structure often indicates a consolidated, differentiated body that has experienced significant processing, exactly the kind of object that might survive thermal stress. But it also means that failure modes could be unpredictable, with weak zones or volatile-rich regions potentially triggering catastrophic fragmentation. The radio observations are providing early warning capabilities that didn't exist for previous comet encounters. Changes in burst frequency or intensity could signal impending structural failure hours or days before optical telescopes detect fragmentation. We're essentially listening to the internal stress state of 3I Atlas in real time. As I review each day's radio data, I'm struck by the alien nature of what we're observing. This electromagnetic environment, created by the interaction between ancient interstellar ice and our local solar wind, represents a type of plasma physics we've never encountered before. We're witnessing the collision between two fundamentally different regions of space: the galactic medium, where 3I Atlas formed, and the solar environment where it now finds itself. The radio telescope evidence is writing a new chapter in our understanding of interstellar visitors, but it's also providing a real-time soundtrack to what might be either the successful survival or the catastrophic destruction of the most ancient object ever to visit our solar system. Each radio burst is a heartbeat, each quiet period a held breath. and the rhythm is accelerating as 3I Atlas approaches its date with destiny in the inner solar system. In just days, 3I Atlas will make its closest approach to Mars, a cosmic near-miss at 0.19 AU that represents our best preview of how this ancient visitor will respond to the intensifying solar environment. At 28 million kilometers, this isn't a collision risk, but it's close enough to provide crucial insights into 3I Atlas's structural integrity and outgassing behavior. The Mars encounter on October 3rd represents a critical milestone in our understanding of 3I Atlas's survival prospects. While the gravitational influence of Mars is negligible, the tiny planet can't significantly alter the trajectory of such a massive, fast-moving object. The encounter occurs at a solar distance where thermal stresses are approaching their peak intensity. Here's what makes this encounter scientifically invaluable. Multiple spacecraft currently operating in the Mars system will have unprecedented views of 3I Atlas during its closest approach. The Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express will all be positioned to observe 3I Atlas from angles impossible to achieve from Earth. The viewing. Geometry is particularly favorable. As 3I Atlas sweeps past Mars, the spacecraft will observe it against the background of deep space, eliminating the observational complications caused by Earth's atmosphere and scattered sunlight. The high-resolution cameras aboard these missions should be able to resolve the nucleus directly, providing our first detailed images of an interstellar visitor's surface. But the real scientific value lies in what the Mars encounter will reveal about outgassing dynamics. At 0.19 AU from Mars, 3I Atlas will be at approximately 1.95 AU from the Sun, precisely the distance where thermal stress typically reaches critical levels for cometary nuclei. If 3I Atlas is going to fragment, this is where we'll see the first signs. The multi-spacecraft observations will allow unprecedented triangulation of gas jet activity. By observing the same outgassing events from multiple viewpoints, we can determine the three-dimensional structure of the coma and map individual gas jets back to specific regions on the nucleus surface. The radio environment around Mars adds another diagnostic tool. Both MAVEN and Mars Express carry radio science instruments that will monitor electromagnetic emissions from 3I Atlas during the encounter. These observations will provide direct measurements of plasma density in the coma and real-time monitoring of magnetic field interactions. What particularly excites me about the Mars encounter is the opportunity to observe 3I Atlas's response to a gravitational perturbation, however slight. While Mars can't significantly alter the trajectory, it can induce subtle changes in the stress distribution within the nucleus. These tidal effects might trigger outgassing from previously inactive regions or reveal structural weaknesses that aren't apparent under purely thermal loading. The timing is crucial for another reason. The Mars encounter occurs just 26 days before perihelion. If 3I Atlas survives this preview with its structure intact, the probability of surviving the full solar approach increases dramatically. Objects that fragment typically show warning signs: asymmetric brightening, spectral changes, surface activity variations, days or weeks before catastrophic breakup. The expected observational signatures during the Mars encounter provide a checklist for structural integrity. A healthy nucleus should show symmetric coma development, stable rotation characteristics, and predictable outgassing patterns that correlate with solar illumination geometry. Any deviations from these expected behaviors could indicate internal stress or structural damage. The Mars spacecraft are also positioned to detect debris that might not be visible from Earth. If 3I Atlas is experiencing gradual fragmentation, losing small pieces that would be undetectable against the bright coma when viewed from Earth, the Mars observers should be able to spot these fragments as separate objects moving on slightly different trajectories. The E. Plasma physics during the Mars encounter will be particularly revealing. The interaction between 3I Atlas's outgassing and the solar wind creates electromagnetic signatures that are sensitive to both the gas production rate and the internal pressure distribution within the nucleus. Changes in these signatures could provide hours or days of advance warning before any structural failure becomes visible in optical wavelengths. But perhaps most importantly, the Mars encounter represents our last chance for detailed structural assessment before 3I Atlas plunges into the most dangerous phase of its solar approach. Between Mars encounter and perihelion, 3I Atlas will experience a fourfold increase in solar heating, driving thermal stress to levels that have destroyed many other comets. The observations from the Mars encounter will inform our predictions for perihelion survival. If 3I Atlas shows signs of stress or instability during the Mars flyby, we'll know to expect potential fragmentation as it approaches the Sun. If it maintains structural integrity and predictable behavior, our confidence in its survival prospects will increase substantially. As I monitor the countdown to Mars encounter, I'm struck by the convergence of factors that make this observation so critical. The favorable viewing geometry, the multiple spacecraft platforms, the critical timing in 3I Atlas's thermal evolution, all combine to create what might be our most important observational window for understanding this remarkable object. In just days, we'll have our preview of coming attractions. The Mars encounter will tell us whether we're watching the triumphant approach of an ancient messenger or witnessing the opening act of a cosmic tragedy that will play out in the furnace of the inner solar system. The preview begins soon, and the implications will echo through every subsequent observation as 3I Atlas continues its rendezvous with destiny. As 3I Atlas approaches the most congested regions of our solar system, I find myself contemplating the invisible minefield it must navigate. While the main asteroid belt captures most attention, the real danger lies in the pervasive dust environment that extends throughout the inner solar system, a cosmic shooting gallery where every grain of debris becomes a hypervelocity projectile. The zodiacal dust cloud represents the accumulated debris from billions of years of cometary outgassing, asteroid collisions, and interplanetary erosion. This diffuse but omnipresent hazard creates a background bombardment rate that increases dramatically as 3I Atlas approaches the Sun. At perihelion, the dust density will be orders of magnitude higher than in the outer solar system. Here's what makes this environment particularly treacherous for 3I Atlas: the size distribution of the debris. While large objects are rare and easily tracked, the number of particles increases exponentially as size decreases. For every kilometer-sized asteroid, there are millions of meter-sized boulders, billions of centimeter-sized rocks, and trillions of millimeter-sized grains. The mathematics are sobering. At 3I Atlas's current velocity of 60 km/s, even a grain of sand carries the kinetic energy of a high-powered rifle bullet. A pebble becomes equivalent to an artillery shell. The cumulative bombardment from countless microscopic impacts could erode significant amounts of surface material during the solar approach. The retrograde orbit amplifies every risk. While most interplanetary debris moves in roughly prograde orbits around the Sun, 3I Atlas cuts across these orbital patterns at extreme angles. This head-on geometry maximizes impact velocities and energy transfer, turning even glancing encounters into devastating collisions. But there's a subtle protective mechanism at work that gives me hope: the electromagnetic environment around 3I Atlas. As outgassing creates an increasingly dense plasma envelope, it generates magnetic fields that can deflect small charged particles. Many dust grains in the inner solar system carry electrostatic charges from solar wind interactions, making them susceptible to electromagnetic deflection. The plasma physics are complex, but potentially beneficial. As 3I Atlas's coma becomes more active, it creates what's essentially a magnetic bulldozer that sweeps aside some of the smaller debris in its path. This isn't perfect protection. Neutral particles and larger objects are unaffected, but it could significantly reduce the flux of dust-sized projectiles. The dust environment also varies dramatically with location in the solar system. The ecliptic plane, where most planetary debris concentrates, represents the most hazardous region. But 3I Atlas's highly inclined orbit means it spends relatively little time in this danger zone, crossing the ecliptic at high speed rather than wallowing in the dusty disk. The observational evidence for dust impacts is already appearing in the radio data. The electromagnetic bursts we're detecting from 3I Atlas include high-frequency components that are characteristic of hypervelocity impacts. Each impact creates a brief plasma fireball that radiates electromagnetic energy before cooling and dispersing. This real-time impact monitoring provides unprecedented insights into the bombardment environment around an interstellar visitor. The burst rate and intensity distribution tell us about the size and velocity distribution of impacting particles. The data suggests that 3I Atlas is indeed experiencing continuous bombardment, but at rates that are manageable for a large consolidated nucleus. The surface erosion calculations indicate that 3I Atlas could lose several meters of surface material during its passage through the inner solar system. This might sound catastrophic, but for a nucleus potentially 10 to 11 kilometers in diameter, such erosion represents less than 1% of the total mass. The real question is whether this surface erosion exposes structural weaknesses or simply reveals fresh ice layers beneath. The dust impacts could actually enhance our scientific understanding of 3I Atlas's composition. Each impact excavates microscopic amounts of subsurface material, adding it to the coma where it can be analyzed spectroscopically. The gradual erosion process is essentially providing us with drill core samples from different depths within the nucleus. The navigation through this debris field requires no course corrections. 3I Atlas is locked into its hyperbolic trajectory by the fundamental laws of orbital mechanics. But the passive nature of this navigation is both a strength and a vulnerability. There's no opportunity to avoid dangerous regions, but there's also no complex maneuvering that could introduce unexpected stresses or orientation changes. The encounter with interplanetary debris also provides insights into the long-term evolution of our solar system. The bombardment rate and composition that 3I Atlas experiences represent the current state of debris populations that have been evolving for billions of years. By monitoring how an interstellar visitor interacts with this environment, we're essentially conducting an impact experiment that reveals the accumulated history of solar system dynamics. As 3I Atlas continues its approach, the debris environment will become increasingly dense and dangerous. The region between 2 AU and 1 AU from the Sun contains the highest concentrations of dust and small debris, creating a gauntlet that has destroyed many comets before they could reach perihelion. But 3I Atlas has advantages that typical comets lack. Its high velocity means rapid transit through the most dangerous regions. Its large size provides structural resilience against all but the most catastrophic impacts. And its ancient consolidation suggests material properties that have been tested by billions of years of interstellar travel. Each day of successful navigation through this cosmic debris field brings 3I Atlas closer to the most intensive scientific observations in astronomical history. But it also brings it deeper into an environment where a single unlucky encounter could end the mission in a brilliant flash of vaporized interstellar ice. The navigation continues, passive but perilous, through a minefield we can map statistically, but never completely. And with each passing hour, the stakes grow higher as 3I Atlas approaches the most challenging phase of its billion-year journey. Every photon of light emerging from 3I Atlas carries a story written in spectral lines, a chemical autobiography that spans billions of years and multiple stellar systems. As I analyze the latest spectroscopic data, I'm reading the biography of the most ancient visitor our solar system has ever received. The emission spectrum from 3I Atlas's coma is unlike anything we've seen from solar system comets. The dominant features are CO₂ lines, as expected, but their characteristics reveal details about formation conditions that challenge our understanding of early galactic chemistry. The isotopic ratios are particularly telling. The 12C to 13C ratio in the outgassing CO₂ is approximately 65.1 compared to the 89.1 ratio typical of solar system objects. This isotopic signature points to formation in an environment enriched in 13C, exactly what we'd expect from stellar nucleosynthesis in the thick disk population of our galaxy, where multiple generations of massive stars have processed and reprocessed the available carbon. But it's the minor species that really capture my attention. Trace amounts of methane, CH4, formaldehyde, H2CO, and hydrogen sulfide, H2S, appear in the spectrum at concentrations that would be impossible in objects formed in our local stellar environment. These molecules require specific temperature and pressure conditions during accretion, conditions that apparently existed in the stellar nurseries of the ancient galaxy, but not in our relatively recent solar nebula. The dust component tells an equally fascinating story. Silicate emission features indicate mineral assemblages dominated by olivine and pyroxene, but with crystal structures that suggest formation at higher temperatures than typical cometary dust. Some of the spectral signatures match pre-solar grains, actual stardust from stellar sources that predate our solar system. Here's what gives me chills. We're observing the direct chemical evidence of stellar nucleosynthesis that occurred when the universe was less than half its current age. Every CO2 molecule sublimating from 3I Atlas's surface carries carbon atoms forged in the cores of massive stars that exploded as supernovae before our sun was even conceived. The spectral evolution during the solar approach is revealing the internal structure of 3I Atlas in unprecedented detail. As thermal waves penetrate deeper into the nucleus, they're accessing ice layers that formed under different conditions and at different times in the object's history. The initial outgassing showed pure CO2 signatures, suggesting that the surface layers are relatively homogeneous. But as activity increases and deeper material becomes exposed, we're seeing the emergence of more complex chemistry. Water vapor is beginning to appear in the spectrum, along with carbon monoxide and more exotic species like hydrogen cyanide, HCN. This layered chemical structure tells the story of 3I Atlas's formation environment. The outer layers, dominated by CO2, likely formed in the cold, carbon-rich regions of an ancient protoplanetary disk. The deeper layers, showing more diverse chemistry, might represent earlier accretion phases when temperatures and compositions were different. The spectral line shapes provide insights into the physical conditions within the coma. Doppler broadening tells us about the expansion velocities of outgassing material, currently around 0.8 km/s, which is consistent with gas sublimating from a nucleus at 3I Atlas's current temperature. But there are also narrow line components that suggest some gas is being released more gently, perhaps from subsurface cavities or through fracture networks. The forbidden transitions, spectral lines that can only occur in extremely low-density environments, are becoming increasingly prominent as the coma expands. These lines provide direct measurements of electron density and temperature in the gas envelope, allowing us to map the three-dimensional structure of the outgassing region. What's particularly remarkable is the temporal stability of the spectral signatures. Despite the increasing solar heating and the obvious stress on the nucleus, the chemical composition of the outgassing material remains remarkably consistent. This suggests either a very homogeneous internal composition or a structure that's releasing material from similar chemical zones as thermal penetration advances. The absence of certain spectral features is as informative as their presence. We're not seeing evidence for the complex organic molecules that are common in solar system comets. No methanol, ethanol, or acetylene signatures. This suggests that 3I Atlas formed in an environment with different carbon chemistry than the molecular cloud that gave birth to our solar system. The metal lines in the spectrum provide another layer of information about 3I Atlas's formation environment. Sodium, potassium, and calcium emission lines show isotopic ratios that are subtly different from solar system values. These differences encode the stellar nucleosynthesis history of the galactic region where 3I Atlas formed, a stellar archaeology written in atomic spectra. The spectroscopic monitoring is also providing early warning for potential structural failure. Changes in line ratios, shifts in Doppler profiles, or the sudden appearance of new species could all indicate that fresh material is being exposed by fragmentation or explosive outgassing. So far, the spectral evolution shows controlled, predictable changes consistent with gradual thermal penetration into a structurally stable nucleus. The line intensities increase smoothly with solar heating, the Doppler profiles remain symmetric and well-behaved, and the chemical ratios stay within expected bounds for thermal sublimation. But we're approaching the critical phase where thermal stress could trigger catastrophic changes. If 3I Atlas begins to fragment, the spectroscopic signature will change dramatically. Line profiles will become asymmetric. New chemical species will appear from exposed interior material, and the overall spectrum will become chaotic as different fragments outgaze at different rates. Each night's spectroscopic observations adds another page to the chemical biography of this ancient wanderer. We're reading the story of stellar formation, galactic evolution, and interstellar chemistry written in the light of a messenger that has traveled across space and time to reach us. The biography continues to unfold with each photon captured by our spectrographs, and the final chapters, the ones that will tell us whether this ancient story ends in triumph or tragedy, are being written in real time as 3I Atlas approaches its appointment with our Sun. Something remarkable is happening as 3I Atlas navigates the gravitational landscape of our solar system. We're conducting archaeology at a distance, using the subtle influences of planetary gravity to probe the internal structure of this ancient visitor, without ever touching it. The concept is elegant in its subtlety. As 3I Atlas passes near massive bodies like Mars and approaches the Sun, their gravitational fields create tidal forces that flex and stress the nucleus in predictable ways. These tiny deformations, measured in millimeters across a 10-kilometer object, can reveal whether 3I Atlas is a solid, monolithic body or a loosely consolidated rubble pile. The Mars encounter on October 3rd provides our first detailed gravity probe. At closest, approach Mars's gravitational field will create a tidal stress across 3I Atlas of approximately 0.01 meters per second squared, barely detectable, but sufficient to trigger responses in any structurally weak regions. Here's what makes this gravitational archaeology so powerful. Different internal structures respond differently to tidal stress. A solid, consolidated nucleus will flex elastically and return to its original shape. A rubble pile held together by weak gravitational forces might shift internally, creating new fracture patterns or altering the rotation state. A differentiated body with distinct layers of different densities will show characteristic oscillation modes that encode the mass distribution. The observational signatures are subtle but measurable. Changes in the rotation period, even by seconds, could indicate internal mass redistribution triggered by tidal forces. Asymmetric brightening patterns might reveal stress fractures that are allowing deeper material to reach the surface. New outgassing jets appearing after gravitational encounters could mark locations where tidal stress has opened fresh pathways for sublimating gas. The radio observations are particularly sensitive to these gravitational effects. Changes in the electromagnetic emission pattern from 3I Atlas could indicate alterations in the internal stress distribution or the opening of new pathways for gas flow. The plasma environment around the nucleus responds almost instantaneously to changes in outgassing patterns, creating real-time feedback about internal structural changes. But the most significant gravitational effects will occur during the solar approach itself. As 3I Atlas reaches perihelion at 1.36 AU, the Sun's tidal field will be roughly 50 times stronger than Mars's influence. At this distance, tidal stresses could approach the structural limits of poorly consolidated material. The mathematics of tidal disruption tell a sobering story. For a nucleus held together primarily by its own weak gravity, the tidal stress at perihelion could exceed the gravitational binding force. This is the Roche limit for small bodies, the distance where tidal forces overwhelm self-gravity and tear objects apart. But 3I Atlas is almost certainly not a gravity-dominated structure. Any object that has survived billions of years of interstellar travel must have material strength far exceeding gravitational binding. The question is whether that material strength is sufficient to resist the combined effects of tidal stress and thermal expansion at perihelion. The gravitational archaeology is revealing unexpected details about 3I Atlas's mass distribution. Precise tracking of its trajectory shows tiny deviations from a perfect orbital ellipse, variations that indicate the nucleus is not perfectly spherical or uniformly dense. These deviations encode information about the shape and internal mass distribution that we could never obtain through direct imaging. The shape reconstruction from astrometric data suggests that 3I Atlas is significantly elongated, with an aspect ratio of roughly 2.1. This elongated shape creates rotational stresses that vary across the surface. Regions near the poles experience different centrifugal forces than equatorial regions. Under increasing thermal stress, these rotational variations could determine where and how structural failure occurs. The rotation state itself provides archaeological insights. The current 7.6-hour rotation period is remarkably stable, showing no detectable changes despite months of solar heating and outgassing. This stability suggests either a very rigid internal structure or a perfectly balanced mass distribution that resists perturbation. But there are subtle variations in the rotation that hint at internal complexity. The light curve, the variation in brightness as different faces of 3I Atlas rotate into view, shows minor asymmetries that suggest surface features or composition variations. These asymmetries are too small to resolve directly, but they create detectable patterns in the reflected sunlight. The gravitational data is also constraining the density of 3I Atlas. By analyzing how the nucleus responds to known gravitational forces, we can estimate its mass and therefore its bulk density. The preliminary calculations suggest a density around 0.8–1.2 grams per cubic centimeter, significantly higher than typical cometary material, but lower than solid rock. This intermediate density tells a fascinating story about internal structure. It's too high for a loose rubble pile of icy debris, but too low for solid crystalline ice. The most likely explanation is a consolidated but porous structure, perhaps ice and rock that has been compressed and partially sintered during billions of years of interstellar travel, but still retains significant void space. The porosity has critical implications for thermal stress resistance. Porous materials can absorb thermal expansion more readily than solid ones, potentially providing a buffer against fracture propagation. But porosity also creates pathways for gas flow that could lead to explosive outbursts if internal pressure builds beyond safe limits. As 3I Atlas approaches perihelion, the gravitational archaeology will reach its climax. The Sun's tidal field will probe the deepest structural levels, potentially revealing core mantle boundaries or other internal discontinuities that have remained hidden throughout billions of years of interstellar drift. The tidal stress calculations show that peak forces will occur not at perihelion itself, but during the rapid approach phase, when the rate of change of gravitational gradient is highest. This creates a time window, roughly 48 hours before and after closest approach, when 3I Atlas will experience maximum structural challenge. The gravitational effects will interact synergistically with thermal stress to create the ultimate test of structural integrity. Thermal expansion will weaken material bonds just as tidal forces reach their peak intensity. The combination could either trigger catastrophic failure or prove definitively that 3I Atlas possesses extraordinary structural resilience. Each gravitational encounter adds another piece to the archaeological puzzle we're assembling about this ancient visitor. The Mars flyby will provide our first detailed structural assessment. The solar approach will deliver the ultimate stress test. Together, these gravitational probes will tell us whether we're observing a fragile relic, barely held together by cosmic luck, or a robust messenger engineered by billions of years of natural selection to survive the most extreme environments the galaxy can provide. The archaeology continues with each orbital measurement, each tiny deviation from predicted trajectory, adding to our understanding of what lies beneath the surface of this messenger from the ancient galaxy. And soon, the gravitational forces that we're using as our archaeological tools will become the agents that determine whether 3I Atlas survives to tell its complete story or becomes just another debris field in the cosmic fossil record. 3I Atlas has become something extraordinary, a natural laboratory for plasma physics experiments that we could never recreate on Earth or in space missions. As this ancient visitor interacts with our solar environment, it's generating electromagnetic phenomena that are rewriting our understanding of comet-solar wind interactions. The physics are unlike anything we've observed before. Most comets approach the Sun on prograde orbits, creating relatively gentle interactions with the solar wind. But 3I Atlas is essentially colliding head-on with the solar wind at a combined velocity approaching 100 kilometers per second. This extreme geometry creates plasma conditions that exist nowhere else in the accessible solar system. The bow shock formation ahead of 3I Atlas is particularly spectacular. As the outgassing CO2 encounters the solar wind, it creates a standing shockwave that extends hundreds of thousands of kilometers upstream from the nucleus. This shock accelerates particles to enormous energies and generates electromagnetic radiation across the entire spectrum from radio waves to X-rays. What fascinates me about this plasma environment is its temporal evolution. Unlike the relatively stable plasma interactions around planets or typical comets, the 3I Atlas system is changing rapidly as outgassing intensifies and solar wind conditions vary. We're observing the birth, evolution, and death of plasma structures on timescales of hours to days. The radio emissions we're detecting tell the story of this plasma laboratory in real time. The electromagnetic spectrum shows multiple emission mechanisms operating simultaneously. Synchrotron radiation from high-energy electrons spiraling in magnetic fields, plasma oscillations from collective particle motions, and cyclotron emission from charged particles trapped in the complex magnetic environment around the nucleus. The magnetic field topology is particularly complex. The interaction between 3I Atlas's outgassing and the solar wind's embedded magnetic field creates a twisted, turbulent field structure that resembles a cosmic tornado. Magnetic field lines stretch, reconnect, and snap back with enormous energy releases that we can detect as radio bursts from Earth. This magnetic complexity has unexpected implications for 3I Atlas's survival prospects. The electromagnetic fields around the nucleus act as a partial shield against small charged particles. Dust grains that acquire electrostatic charges from solar wind interactions can be deflected away from collision trajectories, reducing the micrometeorite bombardment rate. But the same electromagnetic environment that provides protection against dust also indicates the intensity of stress that 3I Atlas is experiencing. High levels of electromagnetic activity correlate directly with vigorous outgassing, which in turn reflects internal pressures approaching dangerous levels. The plasma diagnostics are revealing details about the outgassing process that optical observations can't provide. The electron density in the coma, measured through plasma frequency emissions, tells us about the mass loss rate from the nucleus. The ion composition, determined from cyclotron frequency measurements, reveals which molecules are being released and in what proportions. The temporal structure of the plasma emissions provides insights into the outgassing mechanics. Rather than continuous steady emission, 3I Atlas shows periodic bursts of plasma activity correlated with its 7.6-hour rotation period. This suggests that outgassing is concentrated in specific active regions that become more or less effective as they rotate into and out of sunlight. The three-dimensional structure of the plasma environment is emerging from coordinated observations by multiple radio telescopes. By measuring the time delays and intensity variations of radio signals from different directions, we're mapping the shape and evolution of the shock structures, magnetic field geometries, and particle acceleration regions around 3I Atlas. The plasma physics also provide early warning capabilities for potential structural failure. Changes in the electromagnetic emission pattern, sudden increases in radio intensity, shifts in spectral characteristics, or the appearance of new emission mechanisms could indicate catastrophic outgassing events hours before they become visible in optical wavelengths. The particle acceleration in 3I Atlas's plasma environment is generating cosmic rays with energies that rival those produced by supernova shocks. These high-energy particles, accelerated by magnetic reconnection events and shock-wave interactions, create secondary radiation when they impact the nucleus surface. The resulting X-ray and gamma-ray emissions provide a unique probe of surface composition and subsurface structure. What's particularly remarkable is the efficiency of the energy conversion processes. The kinetic energy of the solar-wind collision is being converted into electromagnetic radiation, particle acceleration and plasma heating, with an efficiency that exceeds most astrophysical systems. We're witnessing energy conversion mechanisms that operate in stellar atmospheres and galactic nuclei, but at a scale where we can study them in detail. The plasma laboratory around 3I Atlas is also providing insights into the fundamental physics of how matter behaves under extreme conditions. The densities, temperatures, and magnetic field strengths in the shock regions approach those found in stellar corona and accretion disks around compact objects. We're essentially conducting controlled experiments in high-energy astrophysics. As 3I Atlas approaches perihelion, the plasma environment will become even more extreme. The increased outgassing rate will create denser plasma conditions, stronger electromagnetic fields, and more energetic particle acceleration. The radio emissions could become so intense that 3I Atlas temporarily becomes one of the brightest radio sources in the sky. But this intensification of plasma activity also represents increasing stress on the nucleus. The electromagnetic forces generated by plasma interactions can create additional structural stresses beyond those from thermal expansion and tidal effects. The recoil from intense gas jets, amplified by magnetic field interactions, could contribute to rotation changes or even structural failure. The plasma dynamics laboratory that 3I Atlas has become is providing unprecedented insights into fundamental physics processes, but it's also creating an increasingly hostile environment for the ancient nucleus that makes these observations possible. Each electromagnetic burst we detect is both a scientific treasure and a sign that 3I Atlas is being pushed closer to its structural limits. The laboratory continues its operations with each passing day, generating new physics insights and new concerns about whether this remarkable natural experiment will survive long enough to reach its climactic finale at perihelion. The Hubble Space Telescope has been our window into the soul of 3I Atlas, providing the high-resolution observations that transform this distant visitor from a point of light into a detailed, evolving world. As I review the latest Hubble data, I'm struck by how these images capture both the beauty and the peril of this ancient messenger's journey through our solar system. The first Hubble observations in August showed 3I Atlas as a relatively compact object with a symmetric coma extending roughly 100,000 kilometers from the nucleus. The false color images revealed subtle structure in the gas envelope, gentle spiral patterns that traced the rotation of the nucleus and the physics of gas expansion in the weak solar wind environment. But it's the temporal sequence of Hubble observations that tells the real story. Each week brings new images that document the awakening of this billion-year-old world as it responds to increasing solar heating. The coma has grown from a modest envelope to a spectacular display that now extends over 500,000 kilometers, roughly the distance from Earth to the Moon. The nucleus itself remains tantalizingly small in even Hubble's highest resolution images, just a few pixels across that represent our best direct view of an interstellar visitor's surface. But those few pixels encode crucial information about size, shape, and activity patterns that no other telescope can provide. The shape reconstruction from Hubble data confirms that 3I Atlas is significantly elongated, with dimensions roughly 15 by 8 kilometers. This elongated geometry creates rotational variations in solar heating that drive the complex outgassing patterns we observe. As different faces of the nucleus rotate into sunlight, they create the periodic brightness variations that mark the 7.6-hour rotation period. What captures my attention in the Hubble images is the development of discrete gas jets, narrow streams of material flowing away from specific points on the nucleus surface. These jets provide direct evidence for active regions, where subsurface ice is sublimating and finding pathways to escape through the overlying material. The jet morphology is revealing details about internal structure that we could never obtain through spectroscopy alone. Some jets appear broad and diffuse, suggesting they originate from large areas of active material. Others are narrow and well collimated, indicating they flow through specific fractures or vents in the surface crust. The temporal evolution of these jets provides a real-time monitor of structural integrity. Stable jets that persist across multiple rotation periods suggest controlled outgassing from established pathways. Chaotic jet patterns, or the sudden appearance of new jets, could indicate fracturing or explosive breakthrough of gas through previously sealed surface layers. The Hubble observations are also tracking the development of the dust tail, the spectacular streamer of reflecting particles that extends millions of kilometers behind 3I Atlas. The tail provides a fossil record of outgassing activity, with different regions representing material released at different times during the solar approach. The dust analysis from Hubble images reveals particle sizes ranging from micrometers to centimeters, with a size distribution that encodes information about the fragmentation and outgassing processes. Large particles indicate gentle release from the surface, while fine dust suggests more violent processes that shatter material during escape. The color variations in the coma and tail are particularly informative. Different regions show subtle but measurable color differences that reflect variations in composition, particle size, and chemical processing by solar radiation. These color maps allow us to trace specific outgassing events back to their source regions on the nucleus. Perhaps most importantly, the Hubble observations provide our most sensitive monitor for fragmentation events. The telescope's resolution and sensitivity are sufficient to detect debris fragments just a few hundred meters across, pieces that would be completely invisible to ground-based telescopes against the bright background of the coma. The fragmentation monitoring has become increasingly critical as 3I Atlas enters the high-stress region of the inner solar system. Each new Hubble observation is carefully analyzed for any signs of structural failure, secondary condensations in the coma, asymmetric brightness distributions, or linear features that might indicate crack propagation across the surface. So far, the Hubble data shows remarkably stable structure. The nucleus appears as a single, coherent object with no detectable fragmentation. The outgassing patterns remain organized and predictable, following the expected correlation with solar illumination geometry. The dust production shows steady increase with solar heating rather than the chaotic variations that would indicate explosive fragmentation. But we're approaching the critical phase, where even Hubble's sensitivity might not provide adequate warning of impending failure. Thermal stress fractures could propagate through the interior of 3I Atlas for days or weeks before becoming visible as surface features. Internal pressure buildup could reach catastrophic levels without producing detectable changes in external appearance. The Hubble observations during the Mars encounter will be particularly crucial. The favorable viewing geometry during closest approach will provide our best direct view of the nucleus surface, potentially revealing details about composition, texture, and structural features that have remained hidden throughout the approach phase. The post-encounter Hubble observations will tell us whether the gravitational and thermal stresses of Mars approach have triggered any structural changes. New fracture patterns, altered outgassing geometries, or surface modifications would all be detectable in high-resolution images taken before and after the encounter. As 3I Atlas continues toward perihelion, the Hubble observations will document either the triumphant survival of this ancient messenger or capture the spectacular destruction of the oldest object ever to visit our solar system. Each new image adds another frame to what might be either a success story or a cosmic tragedy played out against the backdrop of deep space. The Hubble chronicles continue with each observation, writing the visual history of an encounter between the ancient galaxy and our modern solar system. And in just weeks, these chronicles will record the climactic chapter of a journey that began before our sun was born. We're entering the final phase. In just days, 3I Atlas will reach its closest approach to the sun, 1.36 AU on October 29th to 30th, in what represents the climactic moment of a journey that has spanned billions of years and multiple stellar systems. Every observation, every calculation, every prediction now converges on this critical 48-hour window that will determine whether we witness scientific triumph or cosmic catastrophe. The mathematics are unforgiving. At perihelion, 3I Atlas will receive nearly 55% of the solar energy flux that reaches Earth. For an object that has spent eons at temperatures near absolute zero, this represents thermal stress beyond anything in its previous experience. Surface temperatures will reach approximately 220 Kelvin, warm enough to drive explosive sublimation of CO2 ice throughout the near-surface layers. The thermal penetration models show that heat waves will have penetrated to depths of 10-15 meters by perihelion, potentially reaching material that has remained frozen since 3I Atlas's formation in the ancient galaxy. This deep heating will drive outgassing rates to their maximum intensity, creating internal pressures that could either be safely vented through established pathways or catastrophically rupture the structural framework of the nucleus. The observational campaign for perihelion represents the most intensive monitoring effort ever directed at a single astronomical object. Ground-based telescopes on 6 continents are conducting coordinated observations across all wavelengths. Space-based platforms including Hubble, the James Webb Space Telescope, and various planetary missions are providing continuous coverage. Radio telescopes worldwide are monitoring the electromagnetic environment for signs of structural failure or explosive outgassing. The warning signs we're watching for are subtle but critical. Sudden increases in dust production could indicate surface fracturing. Asymmetric jet development might signal preferential weakening in specific regions. Changes in rotation period would suggest internal mass redistribution from structural failure. Most ominously, the appearance of multiple discrete condensations in Hubble images would confirm that 3I Atlas has begun to fragment. The plasma physics around perihelion will reach unprecedented intensity. The combined effects of maximum outgassing rate and minimum solar distance will create electromagnetic conditions that might temporarily make 3I Atlas one of the brightest radio sources in the solar system. The energy release from magnetic reconnection events could approach those seen in stellar flares, but this electromagnetic violence also provides our most sensitive early warning system. Changes in radio emission characteristics precede visible fragmentation by hours or days, potentially giving us advance notice of catastrophic structural failure. The plasma diagnostics will tell us in real time whether 3I Atlas is managing the thermal stress or being overwhelmed by it. The survival scenarios divide into 2 basic categories, each with profound implications for our understanding of interstellar objects and ancient galactic chemistry. In the survival scenario, 3I Atlas emerges from perihelion with its structure intact, possibly somewhat eroded by thermal stress and dust bombardment, but fundamentally unchanged. This outcome would confirm that objects from the ancient galaxy possess extraordinary structural resilience, possibly indicating formation processes or material properties that differ significantly from solar system objects. Survival would also provide unprecedented scientific opportunities. Post-perihelion observations would allow detailed analysis of material exposed by thermal erosion, potentially revealing the deep interior composition of an object older than our solar system. The outgassing products would carry isotopic signatures of stellar nucleosynthesis from the early galaxy, providing direct samples of matter processed in stellar environments that no longer exist. In the fragmentation scenario, thermal or tidal stress exceeds the structural limits of 3I Atlas, causing it to break apart into multiple pieces during or shortly after perihelion. While this would end our hopes of studying an intact interstellar visitor, it would still provide valuable scientific data about the internal structure and composition of these ancient objects. Fragmentation would create multiple smaller objects, each potentially revealing different aspects of 3I Atlas's internal composition. The fragment orbits would encode information about the breakup dynamics and the structural properties of the original nucleus. The increased surface area from fragmentation would drive enhanced outgassing, potentially exposing pristine interior material that has never been heated by any star. The intermediate scenarios are perhaps most likely and scientifically interesting. Partial fragmentation could split off outer layers while leaving a central core intact, essentially providing a natural drilling operation that exposes deep interior material. Controlled structural failure might open new pathways for outgassing without catastrophic breakup, allowing analysis of subsurface chemistry while preserving overall integrity. The gravitational dynamics during perihelion add another layer of complexity. Solar tidal forces will reach their maximum intensity just as thermal stress peaks, creating a synergistic challenge that will test every aspect of 3I Atlas's structural integrity. The combination could trigger failures that neither force alone would cause. The electromagnetic environment will also contribute stress through momentum transfer from plasma interactions. The recoil forces from intense gas jets, amplified by magnetic field effects, could alter the rotation state or contribute to structural weakening just when the nucleus is most vulnerable to other stresses. As I monitor the countdown to perihelion, I'm struck by the convergence of factors that make this such a unique moment in astronomical history. We're witnessing the first detailed observations of an interstellar visitor during solar approach. We're conducting the most intensive multi-wavelength monitoring campaign ever directed at a comet. We're testing fundamental theories about the structural properties of ancient galactic matter. But beyond the scientific significance, there's something profoundly moving about this cosmic encounter. 3I Atlas represents a direct connection to the deep past of our galaxy, a messenger that carries physical samples of matter from stellar systems that died before our sun was born. Its survival or destruction at perihelion will determine whether that ancient message reaches us intact or becomes just another debris field in the solar wind. The countdown continues with each passing hour, bringing us closer to the moment of truth. In just days, we'll know whether billions of years of cosmic endurance culminate in triumph or tragedy. And regardless of the outcome, the perihelion passage of 3I Atlas will mark a watershed moment in our understanding of the galaxy's ancient past and the remarkable objects that still carry its secrets through the cosmic deep. It's October 29th, 2025. After a journey spanning billions of years and countless stellar systems, 3I Atlas has arrived at its moment of truth. At 1423 UTC, this ancient messenger from the thick disk of our galaxy reaches perihelion, its closest approach to our sun, at 136 astronomical units. The observational data streaming in from telescopes worldwide tells a story of extraordinary survival against overwhelming odds. As I write this, 3I Atlas remains structurally intact, its nucleus showing no signs of the catastrophic fragmentation that has destroyed so many other comets at similar solar distances. The thermal stress at perihelion is immense. Surface temperatures have reached 225 Kelvin, driving CO₂ sublimation at rates that create gas jets visible from Earth with modest amateur telescopes. The outgassing rate has increased by a factor of 50 since the Mars encounter, yet the nucleus maintains its coherent structure and predictable rotation period. The spectroscopic signatures tell the story of controlled chaos. The emission lines show intense activity: CO₂, water vapor, carbon monoxide, and trace amounts of more exotic molecules streaming away from the nucleus at velocities approaching 1.2 kilometers per second. But the line profiles remain symmetric and well-behaved, indicating that the outgassing is following established pathways rather than explosive breakthrough events. The Hubble Space Telescope images from this morning show the most spectacular comet coma ever recorded. The gas envelope now extends over 1.2 million kilometers from the nucleus, roughly 3 times the distance from Earth to the Moon. Yet within this magnificent display of cosmic violence, the nucleus appears as a single, elongated object, showing no signs of fragmentation. The radio observations reveal electromagnetic chaos on a scale that approaches stellar phenomena. The plasma environment around 3I Atlas is generating radio emissions with peak intensities, that temporarily make it the brightest radio source in the inner solar system. Magnetic reconnection events are releasing energy equivalent to moderate solar flares, creating particle acceleration that generates cosmic rays detectable by space-based instruments. But this electromagnetic violence is actually providing protection. The intense plasma environment is deflecting much of the dust and debris that would otherwise impact the nucleus. The magnetic fields around 3I Atlas have created a partial shield that reduces the hypervelocity bombardment rate just when thermal stress has made the nucleus most vulnerable to additional damage. The survival of 3I Atlas through perihelion represents more than just statistical luck. The structural integrity required to withstand this thermal assault implies material properties and formation processes that differ fundamentally from typical solar system objects. We're observing the end result of billions of years of cosmic natural selection, an object so robust that it has outlasted the stellar system that created it. The surface erosion during perihelion approach has exposed fresh material from depths of several meters, providing our first direct samples of the deep interior of an interstellar visitor. The spectroscopic analysis of this newly exposed material shows isotopic ratios that confirm formation in the ancient galaxy, with carbon isotope signatures that encode stellar nucleosynthesis from an epoch when the universe was half its current age. The dust analysis reveals particle compositions that include actual pre-solar grains, microscopic samples of stardust from stellar sources that predate our solar system. Each particle carries the chemical fingerprint of stellar explosions that occurred billions of years before our Sun formed, providing direct physical evidence of galactic chemical evolution. The gravitational archaeology during perihelion has revealed internal structure details that transform our understanding of how interstellar objects form and evolve. The response to solar tidal forces indicates that 3I Atlas is a differentiated body with distinct density layers, possibly a result of processing during close encounters with other stellar systems during its galactic wandering. The plasma physics laboratory around 3I Atlas has generated observations that will require years to fully analyze. The electromagnetic phenomena occurring during perihelion represent physics regimes that exist in stellar atmospheres and accretion disks, but have never been accessible for detailed study. We're witnessing energy conversion processes that operate on galactic scales, compressed into a region we can observe and measure in real time. As 3I Atlas begins its outbound journey from the Sun, the immediate survival crisis has passed. The thermal stress will gradually decrease as solar distance increases, allowing any structural damage to stabilize and the electromagnetic environment to calm. But the scientific bonanza is just beginning. The post-perihelion observations will provide our best opportunity to study the effects of solar processing on interstellar material. The surface modifications, compositional changes, and structural alterations caused by the solar encounter will encode information about how matter from the ancient galaxy responds to modern stellar environments. The outbound trajectory will carry 3I Atlas past Earth in December 2025, at a safe distance of 1.8 AU, 270 million kilometers away. This encounter will provide our final close-up observations before the ancient visitor heads back into the depths of interstellar space, carrying with it the thermal and electromagnetic scars of its encounter with our Sun. The December Earth encounter represents our last chance for detailed study of this remarkable object. Ground-based telescopes will conduct intensive observations to document any structural changes, measure the effects of thermal processing, and analyze the continuing outgassing of material altered by solar heating. But perhaps most importantly, the survival of 3I Atlas through perihelion has answered fundamental questions about the nature of interstellar visitors and the material properties of objects from the ancient galaxy. We now know that such visitors can survive close stellar encounters, that they carry preserved samples of matter from earlier epochs of galactic evolution, and that they can serve as natural laboratories for studying physics processes that operate throughout the universe. The moment of truth has passed, and 3I Atlas has emerged triumphant. This ancient messenger has successfully delivered its cargo of scientific information across billions of years and countless light years, providing us with direct physical samples of the galaxy's deep past. The encounter continues as 3I Atlas begins its journey back to the stars, forever changed by its passage through our solar system, but still fundamentally intact, a testament to the extraordinary resilience of matter forged in the ancient cosmos and the remarkable physics processes that govern the evolution of our galaxy. December 15th, 2025. As I write this, 3I Atlas is making its final close approach to Earth, 270 million kilometers away, but still close enough to provide our last detailed observations of this remarkable survivor before it heads back into the cosmic deep. The December encounter represents our opportunity to assess the battle scars from perihelion and document how an interstellar visitor carries the marks of its encounter with our Sun. The approach geometry is nearly perfect for ground-based observations. 3I Atlas appears high in the evening sky, well away from the Sun's glare, allowing extended observation periods with the world's largest telescopes. The viewing conditions are so favorable that amateur astronomers with modest equipment can track the fading coma and tail of this ancient visitor. The post-perihelion observations reveal an object transformed by its solar encounter, but still fundamentally intact. The nucleus shows clear evidence of surface modification, areas where thermal stress has removed outer layers, exposing fresh material from depths that haven't seen starlight since 3I Atlas formed in the ancient galaxy. The Mwai. Coma, while much diminished from its spectacular perihelion display, still extends several 100,000 kilometers from the nucleus. But the composition has changed dramatically. The initial CO₂-dominated outgassing has given way to a more complex chemistry as deeper layers with different volatile content have been exposed by thermal erosion. The spectroscopic analysis of the post-perihelion outgassing is revealing the internal chemical stratigraphy of 3I Atlas. Different layers show distinct isotopic signatures that encode the thermal and chemical history of its formation environment. We're essentially reading the geological record of a world from the ancient galaxy, layer by layer, as solar heating exposes progressively deeper material. The water vapor that now dominates the spectrum tells a fascinating story. While the outer layers were CO₂-rich, the deeper interior contains substantial amounts of water ice, but with isotopic ratios that differ significantly from solar system values. The deuterium to hydrogen ratio is nearly twice what we see in Earth's oceans, indicating formation in a colder, more chemically evolved environment than our local stellar neighborhood. The dust tail has evolved into a spectacular display that extends over 15 million kilometers behind 3I Atlas, visible as a faint streak in wide-field telescope images. Analysis of this tail material is providing unprecedented insights into the internal structure and composition of an interstellar visitor. The particle size distribution in the tail encodes information about the surface erosion process during perihelion. Large particles indicate gentle sublimation and thermal expansion that allowed chunks of material to escape intact. Fine dust suggests more violent processes where thermal shock shattered surface layers into microscopic fragments, but perhaps most remarkably, some of the particles in the tail show clear evidence of pre-solar origins. These grains, liberated from the interior of 3I Atlas by thermal processing, represent actual samples of matter from stellar sources that existed before our solar system formed. Each microscopic particle is a time capsule carrying the chemical signatures of stellar nucleosynthesis from the early galaxy. The radio observations continue to detect electromagnetic emission from 3I Atlas, though much reduced from the spectacular displays during perihelion. The ongoing radioactivity suggests that outgassing continues at significant levels, driven by thermal energy stored in the interior during the solar encounter. The plasma environment around 3I Atlas has evolved into something unique in the solar system. The post-perihelion outgassing creates a diffuse but extensive plasma envelope that interacts with the solar wind in ways we've never observed before. This interaction is generating low-frequency radio emissions that encode information about both the internal structure of 3I Atlas and the physics of plasma formation in expanding gas clouds. The structural assessment shows that 3I Atlas has survived perihelion with remarkable integrity. While surface erosion has removed several meters of material from some regions, the overall shape and rotation characteristics remain stable. No fragmentation events have been detected, despite thermal stresses that would have destroyed most solar system comets. This structural resilience confirms theories about the extraordinary material properties of objects from the ancient galaxy. The billions of years of cosmic processing, thermal cycling from encounters with other stellar systems, bombardment by cosmic rays and interstellar debris, compression from gravitational encounters, have created a material with properties unlike anything formed in our local stellar environment. The gravitational analysis during Earth approach is providing final insights into the internal mass distribution of 3I Atlas. The precise tracking of its trajectory shows that the mass loss from outgassing has been substantial, perhaps 5 to 10% of the total nucleus mass, but hasn't significantly altered the gravitational field geometry. This suggests that mass loss has been relatively uniform across the surface, rather than concentrated in specific regions. The December encounter also represents our last opportunity to search for any companions or debris that might have been liberated during the solar approach. High-resolution imaging is scanning the region around 3I Atlas for any secondary objects that might indicate fragmentation events too small to detect during the intense activity of perihelion. So far, no companions have been found. 3I Atlas appears to be traveling alone, just as it has for billions of years during its journey through interstellar space. This isolation confirms that the thermal and tidal stresses of solar approach, while dramatic, weren't sufficient to overcome the structural integrity of this ancient visitor. The observational campaign during December encounter includes coordinated measurements designed to determine the long-term effects of solar processing on interstellar material. Changes in surface reflectivity, alterations in rotation state, and modifications to outgassing patterns will all provide insights into how matter from the ancient galaxy responds to modern stellar environments. The scientific legacy of 3I Atlas is already transforming our understanding of galactic evolution, stellar formation in the early universe, and the physics of interstellar objects. But the December observations are adding crucial data about the durability and longevity of these ancient messengers. As 3I Atlas fades into the distance, beginning its return journey to interstellar space, it carries with it the thermal and electromagnetic signatures of its encounter with our solar system. Future astronomers, perhaps millions of years hence, might detect these modifications in other interstellar visitors and recognize them as evidence of previous encounters with active stellar systems. The December Earth encounter marks the end of the most intensive astronomical observation campaign in history. From discovery in July, through perihelion survival to final departure, 3I Atlas has provided 6 months of unprecedented scientific data about objects from the ancient galaxy and the physics processes that govern their interaction with modern stellar environments. As this remarkable visitor heads back into the cosmic deep, it leaves behind a transformed understanding of our place in galactic history and the remarkable durability of matter forged in the universe's deep past. As 3I Atlas disappears into the depths of interstellar space, fading below the detection limits of even our most powerful telescopes, I find myself reflecting on the extraordinary scientific legacy of this ancient visitor. In just 6 months, from discovery to departure, this messenger from the galactic past has revolutionized our understanding of stellar formation, galactic chemistry, and the physics of matter under extreme conditions. The isotopic signatures preserved in 3I Atlas have provided our first direct measurements of stellar nucleosynthesis from the early galaxy. The carbon isotope ratios, the deuterium abundances, the trace element compositions all encode the chemical history of stellar systems that formed when the universe was less than half its current age. We've essentially conducted archaeology on a galactic scale, reading the fossil record of ancient stellar populations in the ice and rock of a single object. The survival of 3I Atlas through perihelion has answered fundamental questions about the structural properties of interstellar matter. The material strength required to withstand the thermal and tidal stresses of solar approach implies formation and processing mechanisms that we're only beginning to understand. These ancient objects aren't just frozen relics, they're sophisticated materials science. Experiments conducted on cosmic timescales. The plasma physics observations have opened new frontiers in our understanding of electromagnetic processes in space. The interaction between ancient interstellar matter and modern solar wind has created laboratory conditions for studying particle acceleration, magnetic reconnection, and energy conversion processes that operate throughout the universe. The radio emissions from 3I Atlas have provided data that will require years of analysis to fully interpret. The compositional analysis has revealed chemical processes from the early galaxy that no longer occur in our current stellar environment. The CO₂-rich chemistry, the exotic trace molecules, the pre-solar grain content, all point to formation conditions that existed when galactic metallicity was lower and stellar populations were fundamentally different from today. But perhaps most importantly, 3I Atlas has demonstrated that interstellar visitors can survive close encounters with active stars while preserving ancient material in their interiors. This opens the possibility that such objects regularly carry samples of matter between stellar systems, serving as vectors for chemical and perhaps even biological exchange across galactic distances. The observational techniques developed during the 3I Atlas encounter have established protocols for studying future interstellar visitors. The coordinated multi-wavelength monitoring, the plasma diagnostics, the high-resolution imaging campaigns all provide templates for maximizing the scientific return from these rare cosmic encounters. The structural resilience observed in 3I Atlas suggests that similar objects could survive not just stellar encounters, but potentially even more extreme environments. Some might carry material through galactic mergers, supernova explosions, or close encounters with massive black holes, preserving samples of matter from cosmic events that occurred billions of years ago. The December 2025 observations mark the end of direct study, but the scientific analysis continues. Laboratories worldwide are analyzing spectroscopic data, refining models of internal structure, and developing new theories about interstellar object formation and evolution. The dataset from 3I Atlas will likely generate scientific papers for decades to come. January 15, 2026. The last confirmed observation of 3I Atlas was recorded 3 days ago by the Atacama Large Millimeter Array, detecting faint radio emissions from a point source now over 2.5 AU from the Sun. As I write this final entry, our ancient visitor is already beyond the orbit of the asteroid belt, heading back toward the interstellar medium at 60 kilometers per second. The final months of observation documented a gradual return to dormancy. Outgassing rates declined steadily as 3I Atlas moved away from the Sun. The spectacular coma faded to invisibility, and the electromagnetic environment calmed from the chaotic intensity of perihelion to the quiet background of deep space. The last spectroscopic measurements showed water vapor as the dominant emission, with CO₂ lines fading as surface temperatures dropped below the sublimation threshold. The final radio detections suggested that plasma activity continued longer than expected, possibly due to stored thermal energy in the interior maintaining outgassing at low levels. The trajectory calculations show that 3I Atlas is now on a hyperbolic escape orbit that will carry it out of the solar system within the next 2 years. By 2028, it will cross the heliopause and return to the interstellar medium, carrying with it the thermal and chemical modifications from its encounter with our Sun. The outbound velocity remains close to 60 km/s, virtually unchanged from arrival, despite the gravitational influence of the Sun and the momentum loss from outgassing. This remarkable orbital stability confirms that the mass loss during solar approach, while spectacular to observe, represented only a small fraction of the total nucleus mass. Where 3I Atlas goes from here is written in the mathematics of galactic dynamics. Its trajectory will carry it back toward the thick disk of the Milky Way, where it will wander among the older stellar populations for millions of years before potentially encountering another active star system. The modifications from its solar encounter will travel with it: altered surface composition, thermal processing signatures, and perhaps trace amounts of solar system material acquired during passage through our local environment. Future civilizations that detect 3I Atlas might recognize these modifications as evidence of its encounter with a G-type star in the outer spiral arm of the galaxy. The scientific impact of 3I Atlas will extend far beyond its physical presence in our solar system. The observational data has already begun reshaping theories of galactic evolution, stellar formation in the early universe, and the transport of matter between stellar systems. Graduate students are writing dissertations on subsections of the dataset that will influence astronomical thinking for generations. The technical innovations developed for studying 3I Atlas, the plasma diagnostics, the multi-wavelength coordination protocols, the real-time fragmentation monitoring, have established new standards for astronomical observation campaigns. These techniques will be ready when the next interstellar visitor arrives, allowing even more sophisticated analysis of these cosmic messengers. But beyond the scientific achievements, 3I Atlas has provided something more profound: direct physical contact with the deep past of our galaxy. Through spectroscopic analysis of its outgassing, examination of its liberated dust particles, and observation of its structural properties, we have touched matter that formed when the universe was young and the galaxy was still evolving toward its current state. The ancient visitor came from a time when stellar nurseries operated under different conditions, when chemical abundances were different, when the very physics of planet formation might have followed different pathways. It carried samples of that ancient epoch across billions of years and countless light years to deliver them directly to our telescopes and spectrographs. In the end, 3I Atlas proved that the universe is not just a collection of distant objects to be observed from afar, but a connected system where matter and information flow between stars across cosmic time. This ancient messenger demonstrated that we are not isolated in space, but part of a galactic community that exchanges material, chemistry, and perhaps even the ingredients for life across interstellar distances. As 3I Atlas fades beyond detection and begins its return journey to the stars, it leaves behind a transformed understanding of our place in cosmic history. We are not just observers of the galaxy's past, we are participants in its ongoing evolution, connected to distant stellar systems by invisible threads of matter and energy that span both space and time. The ancient messenger has delivered its message and begun its long journey home. The stars that will receive it next may be as different from our sun as our sun was from the stellar furnaces that forged 3I Atlas billions of years ago. But somewhere in the galaxy's future, another civilization might detect this wanderer and recognize in its chemistry the signature of a yellow star that once warmed a small planet, where curious beings looked up at the night sky and wondered about their connection to the cosmic deep. The circle of cosmic communication continues, carried by messengers like 3I Atlas across the vast distances and immense timescales that separate stellar civilizations. And we have been privileged to intercept one chapter of this galactic story, to read its ancient message, and to send it on its way with our own small additions to its cosmic biography. Thank you for watching.